Welcome to this explainer. Today, we're taking a fascinating journey right into the hidden architecture of the tech use every single day. We're going to explore exactly how rigid, math-driven machines manage to process vague, subjective human concepts. It's a journey through the fuzzy inference machine, and I promise, by the end of this, you're going to see your smart devices in a completely different light.
Okay, let's dive into this. Here's our structural blueprint for today. 1. The concept of fuzzy logic. 2. What is an FIS? 3. The fuzzy knowledge base. 4. 4 steps of reasoning. And 5. Popular fuzzy system models. Let's get right to it.
Section 1. The concept of fuzzy logic. Before we even look at the machines, we have to talk about a very human problem: blurry data. Think about it. How on earth do computers, which are famously built on strict absolutes, right, ones and zeros, how do they process vague, subjective concepts? I mean, if I ask you to point out all the tall people in a room, you just do it intuitively. But a computer? It panics. Does tall start at exactly 6 feet? What if you're 5'11 3/4? To a traditional machine, there is zero gray area. And that is exactly where fuzzy logic comes in. It's an approach to computing that completely changes the game. Instead of relying on the usual true or false, 1 or 0 Boolean logic, it evaluates data based on degrees of truth. It literally models those gray areas mathematically. It's absolutely crucial because it allows elements to belong partially to a set. You don't have to strictly be tall or not tall. You could have, say, a 70% degree of truth in the tall category. This is what allows systems to handle incredibly nonlinear complex functions. Notice the stark difference in these approaches. Crisp logic is like a staircase, discrete, absolute, 0 or 1. But fuzzy logic, it's more like a smooth ramp. The variables are continuous, sliding anywhere on a scale from 0 to 1. This flexibility is the whole reason we use fuzzy logic when a traditional mathematical model just doesn't exist, or maybe it's just way too complex to run in real time. It actually lets us take the intuition of a human expert and encode it directly into a machine.
Section 2. What is an FIS? Now that we understand the underlying logic, let's look at the actual tool that puts it to work, the Fuzzy Inference System, or FIS. It's a nonlinear mapping process. And this brilliantly illustrates the journey. Raw, precise numerical data, what engineers call crisp input, enters the system. It gets translated by the fuzzifier, evaluated by the inference engine using a set of rules, pushed through a defuzzifier, and then a crisp output comes out the other side. Whether you hear it called a fuzzy model, a fuzzy expert system, or a fuzzy logic controller, this is the universal architecture that turns precise data into fuzzy reasoning and then back into a precise command.
Section 3. The fuzzy knowledge base. Let's crack open that middle box, the real brains of the operation. There are 2 conceptual components that store the system's logic. First up is the rule base. This contains the fuzzy if-then rules that usually come from human experts or numerical data. Think, if the temperature is hot, then make the fan speed fast. The second part is the database, which is basically a dictionary. This defines the membership functions. It lays out the actual mathematical shapes and curves used in those rules. For example, using a trapezoidal membership function, researchers can mathematically divide a curve into sections, like small, medium, and big, to define exactly what hot actually means to the machine.
So, when you put the rule base and the database together, they are jointly referred to as the fuzzy knowledge base. Honestly, this combination is the core intelligence of the whole setup. Without the rules to follow and the dictionary to actually define the terms inside those rules, the inference engine would be flying totally blind when trying to evaluate any input data.
Section 4. 4 steps of reasoning.
We've seen the brains, so let's walk down to the active factory floor where the processing happens. An FIS follows a strict 4-step assembly line sequence. 1. Fuzzification. 2. Rule evaluation. 3. Generating consequence. And finally, 4. Defuzzification. This is the exact flow data takes through the inference engine. Step 1 is fuzzification. Think of the fuzzifier as a translator. It takes a precise, crisp input. Say your smart air conditioner gets a room temperature reading of exactly 72.4 degrees, and it figures out where that sits on those membership curves we just talked about. It translates the raw number into vague linguistic variables. It basically says, all right, 72.4 degrees belongs 40% to the medium or warm category and 60% to the big or hot category. It's assigning degrees of truth. Now, what's really interesting about this pathway is the central inference process. Once those inputs are fuzzified, they activate the linguistic rules. The inference engine determines exactly how those rules fire and combine simultaneously.
This right here is the heart of the reasoning process, where multiple fuzzy rules are evaluated based on the data handed over by our translator.
Inside that inference engine, we hit steps 2 and 3, rule evaluation and generating consequence. The system takes those translated membership values and combines them mathematically, often using a simple minimum function or multiplication. This determines the firing strength, or degree fulfillment for each rule. Basically, it's asking how strongly should this specific rule react to this specific data. Then, depending on that firing strength, the system generates qualified consequence, or outcomes, for every single individual rule that was triggered.
Which brings us to the end of the line. Step 4, defuzzification. The system now has all these fuzzy outcomes from various rules, but it has to actually do something, right? It aggregates all those qualified consequence and converts them back into a single, actionable, crisp output. You might be wondering, why go back to crisp logic? Well, because physical devices, like the motor in your AC or the brakes in your car, they need precise, exact commands to work. You can't tell a motor to spin sort of fast. It needs a specific electrical voltage. Defuzzification gives us that exact number.
Section 5. Popular fuzzy system models.
While that 4-step architecture is universal, the exact mathematical engine inside can vary. Researchers generally rely on 3 popular methods: the Abraham-Mamdani model, the Sugeno model, and the Tsukamoto model. The core differences between them really just come down to how they handle those consequences, how they aggregate the rules, and the specific defuzzification math they use to get that final crisp output.
Introduced back in 1975, the Mamdani method is by far the most commonly used inference model. Its approach is very geometric. It actually chops off the tops of the consequent membership functions using minimums, and then combines them using maximums to create a merged, shaded shape. The final crisp output is usually found by calculating the center of gravity of that combined shape.
Let's move on and see how this builds in the other models, comparing the Tsukamoto and Sugeno mathematical approaches. Instead of dealing with those complex 2D shapes for the consequence like Mamdani does, these models simplify things mathematically. Tsukamoto relies on monotonic functions, meaning curves that always go up or always go down. Sugeno, on the other hand, often skips the fuzzy consequent entirely, replacing it with a straightforward mathematical equation or even just a constant value. Both of these rely heavily on weighted averages at the very end, which makes them highly efficient for computers to calculate rapidly and real-time control systems.
So having walked through this whole architecture together, here is a thought to leave you with. From the washing machine that adjusts its water level based on how dirty your clothes are, to the smart thermostat balancing warm and cool in your living room, which of the smart devices currently operating in your home are quietly running a fuzzy assembly line right now? Understanding the fuzzy inference machine is truly the key to understanding the intuitive magic of modern engineering. Thanks for learning with me today, and keep exploring.